Hey everyone, in this video, I'm going to be going through the project that I've been creating in this tutorial series and comparing it to the version of it that I've been iterating on in between videos. I've made a lot of videos in this series and I've made a lot of different components for this Locomotion system, and since recording each video on each component, I've made a variety of minor adjustments to many of these that result in a much smoother final output for the Locomotion system. So I went ahead and recorded myself going through the project function by function and comparing each of them and making the changes that need to be made to bring the YouTube recording project up to par with the project that I've been developing and iterating on myself. So this video is going to be a long one. In most cases where things were compared and they matched, I did cut those parts of the videos out, but I did treat it as more of a longer one-take style of video. So without further ado, let's get started.
To begin, we are going to upgrade the project from 5.2 to 5.3. If you've been following along in 5.3, then you can skip ahead to the next section. I've been working out of 5.2 thus far, so I'll need to upgrade the project now. When I last tried to upgrade the project, I ran into some issues with some files becoming corrupted in the process. So instead of upgrading this project, I'm going to migrate the assets that we need into a new blank 5.3 project that I've already created. I've just opened it up for the first time, and before I migrate any files into it, I'm going to open up its plugins menu under the Edit tab of the top toolbar. And I'm going to navigate to the animation section and enable the plugins that we need. I'm going to enable the Animation Locomotion Library plugin, the Animation Warping plugin, and I'm now scrolling through to make sure there's not anything else that I'm missing or forgetting. That looks to be everything, so I'll go ahead and restart this project. Now, I'll open the content browser of the DevSchool Anim System project. I'll navigate into the third-person folder, right-click on the third-person character, and migrate it. And this will pull all the assets referenced by the third-person character, and this includes the animation blueprints we've created, and all the files that they reference too. I'll now select OK, and put in the file location for the new project. Open up its content folder and click the select folder button to begin the migration process. Looks like there was a null input modifier on an input action, and that may have caused an issue, so I'm now going to go ahead and check that in the new project. We have the files that we need in, and I'll go ahead and navigate into the inputs folder. And I'll remove this extra modifier. Now I'll go ahead and open up the project settings for the new project. And I'm going to make my way over to the Maps and Modes section and change the editor startup map to the third-person map that should have migrated in. Looks like that map wasn't being referenced by any of the assets, so I'm going to need to migrate that separately. Back in the old project, I'm going to right-click on the third-person map and migrate it. We already have our new project selected in the file browser, and I'm going to not overwrite the assets that we've already migrated, that are being migrated along with the map this time around. We can now enter into the third-person map. I'll open up the project settings again, back to Maps and Modes, and now we should have the third-person map that we can select. Now this will be the default editor startup map. If I play, we should have our character and the locomotion system should be working properly, which it appears to be. To begin, I'm going to navigate over into the base animation blueprint. I'll go to Blueprint Thread Safe Update Animation, and now I'm going to compare the implementation in this project to my most up-to-date project, and I'm going to continue to do this for each of the functions until I find a place where they do not match. Alright, the first change that we are going to make is in the get acceleration data function. Right now we're dividing this vector by delta time, which should always have a value. However, when we're not playing, it has a value of 0, and thus we're getting all sorts of warnings as it's attempting to divide by 0 while we have the animation blueprint open. So what I'm going to do is split this pin and get some safe divide nodes here. 3 to be exact. And I'm going to divide each float component of the vector by delta time individually. I'm now going to split the struct pin of this set node and plug in each safe divide node into one of these components. Next, we can optimize our logic here where we set our relative acceleration variable. I'm going to grab this isAccelerating boolean that's plugged into the branch currently, and I'm going to get a select node when I drag out from it. I'm going to get both of our property access nodes here, one that gets the max acceleration and one that gets the max deceleration. I'm going to plug max deceleration into false and max acceleration into true. So instead of changing which one of these we're using based on a branch, we're just going to use a select node and only get one and essentially have the complexity of this section of the blueprint. I'll go ahead and grab these nodes here, copy and paste them down here, and organize them some. I'm going to delete the current get max braking deceleration that we just copied so that I can plug in the result of the select node into the vector clamp size max node. Here we have another divide node. I'm going to get 3 safe divides again to just be extra careful here instead of dividing a vector by a float again, even if that float should never be 0. And now we are going to divide by the result of the select node. I'm going to get a reroute here to clean things up a bit. I'll split the struct pin on the unrotate vector, and I'm going to move these down and try to compact this a little bit more than it is so far, and plug the float pins in. Now we can plug the execution pin from the set physical acceleration variable into the set relative acceleration amount variable. Oops. Okay, and now I will delete the old section of code and move the new one up and in. Next, I'm going to rework some of the logic in the update orientation data function. I'm going to disconnect where we calculate our locomotion direction and make the graph a bit easier to read and rework the hip-facing direction setting logic slightly. I'm going to first get a sequence node that I'll plug into the set acceleration locomotion angle value. Off of the then 0 pin, I'll plug in our first calculate locomotion direction that takes in our locomotion angle. Additionally, instead of plugging our locomotion angle in, I'm going to swap that out for the locomotion angle with offsets variable. Go ahead and move the nodes that set the previous locomotion direction and the current locomotion direction, and I'm going to disconnect the next calculate locomotion direction that is based on acceleration. I'll move it down and plug it into the second pin of the sequence. And now I'm going to disconnect the struct for the locomotion direction settings, drag out from it, and promote it to a variable, which I am going to name locomotion direction profile. I'll now bring the variable in. I'm now going to give it the following values: -45 for forward min, 45 for forward max, -135 for backward min, 135 for backwards max. Now, I'm going to make a change to this struct. I'm going to separate out the dead zone into a forward-backward dead zone and a right-left dead zone. So I'll add f/b into the name of this dead zone, and I'll add a new float variable, which is going to be r/l dead zone. I'll save, close out of that, recompile, and now the forward/backward dead zone is going to be 10, and the right/left dead zone is going to be 0. At least for my current implementation. I'll delete these old nodes and plug this new variable in to each of the calculate locomotion direction nodes. Next, we have our logic to set the hip facing direction. I'm going to create a branch here, and I'm going to create a new Boolean variable, and I'm going to name it enable variable hip facing. I'm going to compile and set this to true. And what this is going to allow us to do is it's going to allow us to rework some things so that the spin state can be toggled on and off. And that way, if you have animations that you're using with the system that do not have spin animations, such as the Lyra animations, you can use them with the exact same project without modifications by being able to toggle variable hip facing. If enable variable hip facing is false, we are going to set the hip facing direction. And what we're going to do is we're going to set it from the desired hip facing variable. We're going to find the desired direction based on the locomotion direction enumeration. And so if you're using the Lyra animations, for example, you would set your desired hip facing to match the animations that you're using. In that case, left would be backwards, right would be forward, backward would be backwards, and forward would be forward. Next, off of the true pin, we're going to reuse this selection logic here. we're going to get the hip facing curve value, check if it is greater than 0, and check if it is equal to 0. If it is greater than 0, we'll return forward. If that is false, we'll return backwards. And if it is equal to 0, then we are going to use the current hip facing direction, as there is not a curve in the animation to override and have it change. Next, I'll plug the true pin of this branch into the set hip facing direction variable node. Now we need to make some updates to our calculate locomotion direction function, as we've changed the way our locomotion direction profile struct works. I'm going to remove the dead zone logic that we created previously connected to the first pin of this sequence node. I'm going to remove the sequence node. I'm going to plug the calculate locomotion direction input node into the first branch that we have here. And I'm going to go ahead and delete the rest of the logic, so the rest of the branches here, and just focus on this first branch in the way that we're going to be changing things. So let's look at the settings struct in isolation here. I'm going to get the forward minimum value and subtract the forward backward dead zone from it. Next, I'm going to get the forward max value, and I'm going to add the forward backwards dead zone to it. I'm going to plug the result of the subtraction into the minimum input of the in-range function, and the addition result into the maximum input. The current locomotion angle will be the value input, and the return value will plug directly into the branch here. I'll get rid of the not node. And we're going to return forward in the return node here. I'm now going to copy this grouping of nodes 3 times. Now I'm just lining them up. And I'll plug the false of each branch into the subsequent branch. For the second grouping of nodes, we're going to use the backward min and plug that into the addition, and the backward max, which we're going to plug into the subtraction. The subtraction is going to go into the max input of the in-range, and the addition result is going to go into the min input. And this is going to create the backward range that we're going to check whether or not we are within. And we're actually going to add a not node into this. So this logic here is checking if we're anywhere except for backwards. And if that's not true, we must be in the backwards range, and thus we're going to return the backwards enumeration. I'm going to get another return node. This time we're going to return right. This time, forward max is going to go into the subtraction, and backward max is going to go into the addition. Additionally, we're going to plug I actually made a mistake and plugged the forward max into the wrong pin. This needs to go into the top pin. And we're going to use the right and left dead zone for the bottom pins of both of these nodes. Finally, we're going to return left off of the last branch. And for this one, we're going to plug forward min into the addition node and backward min into the subtraction node. Alright, that should be it for the direction. We should compile successfully, and now I'm going to take a moment to test and make sure that I did everything properly. If I did, the directions should still work properly, and animations should still be selected properly. And that does appear to be the case. We can now move on to the update character state data function and see if there's anything that we need to change there. These match up properly. Finally, we have the update root yaw offset data function. And the set root yaw offsets function. We actually do not need this previous root yaw offset variable. I'll delete it out. And I'll delete the variable itself as well. We do not make use of the variable anywhere else. I thought that we would need it when I put this function together, but I was incorrect. That is going to be it for Blueprint Thread Safe Update Animation. And that is all the functions that we call within here. So now let's go ahead and move over into our animation graph. The first thing I'm going to do is copy the additives that we are applying here. I'm going to open up the Locomotion layers blueprint and enter into the full body jump additive layer. We're going to combine all of our additives into this layer and rename it to full body additives. I'll go ahead and open up the animation layer interface and rename this to full body additives. And I'm going to add an input pose. Compile, save. I'll take this input pose, move it over here, and paste in our logic from our main blueprint's animation graph. We're going to apply the lean acceleration additive first with an apply additive node. So I'll plug the input pose into the base input of this node. Next, I'm going to get a property access node. And I'm going to get to the relative acceleration amount variable from the main animation blueprint. I'm going to split the struct pin. We'll now plug the property access value into the appropriate pins. And these need to be swizzled around, so the X value into forward backward and the Y value into left right. Next, we will go ahead and apply our jump additive state machine with a new apply additive node. Next, I'll get our look aim offset and plug in the base pose. And I'll get a new property access node to get the root yaw offset from the main animation blueprint. I'll additionally copy this to get the aim pitch. And I'll plug the result of this aim offset into the output pose. I'll compile, and back in the base animation blueprint, and back in the main animation graph, we can disconnect where we're applying our additives and delete these nodes out. Next, I'll get the saved pose for Locomotion, plug that into the full body additives, and plug that into the blend poses 0 for the layered blend per bone that we have here. Next, I'm going to replace the inertialization node with a new type of inertialized blending named dead blending, which will result in a much higher quality blend. Dead blending will allow for inertialized blends just between states. So when you have a lot of rapid state transitions in a state machine, dead blending can keep up, while inertialization will fall behind and create sort of popping poses. So you can do longer blends as multiple states are being switched between and still keep the inertialized blending functioning. Next, we have our foot placement node. I'm going to compare the settings in these to make sure that I have them aligned properly between both of these projects. I'm going to change the speed threshold to 60. The lock type to unlocked. The replant radius ratio to 0.6. The max extension ratio to 0.3. And under interpolation settings, I'm going to change the floor linear stiffness to 2000. I'll go ahead and compile, and now we can move into our Locomotion state machine. I'll begin by reworking the transitions to make sure they all match my most up-to-date project. Let's start with the idle to start transition. We're checking if the character is accelerating, we're using an inertialized blend, and we're going to use a duration of 0.3. Next, we have the start to cycle rule. This first one here is one that I am going to update. Now, I found that this distance threshold did not work too well, and I was just always opting for the velocity one. So I'm going to pull this out, and instead I'm just going to get a was anim notify state active in source state node. I'll plug the return value into the false input of the select node, and I'll choose the ans underscore exit state animation notify. And now in our unarmed upright strafing animation set animations and the starts, we are going to make sure that we have that animation notify placed into all of these at the ends. I'll go ahead and add it in now. We chose a duration for this transition that was 0.3, I believe. Yes, 0.3 is the time there. And I think those footsteps might have been coming through quite loud, so I apologize for that. I just turned down my desktop audio in my recording software, so that should not interfere with my voice any longer. I'll go ahead and add the exit state notify state, bring it up to the end, and try to get this close to 0.3 seconds. And I'll zoom in as I need to. There we go. I can now copy this and paste it into each of these start animations. And you do not need to mind the exit anim notify. That was something I was messing around with at an earlier time, and it is not relevant to the series or the system. And I'm going to do the same thing with the walk animations. For starting, I'll open them all up and paste in that animation notify state. Back in our base animation blueprint, I'm going to set all of these transitions to use a duration of 0.3 and to be inertialized. Next, let's look at the start to stop and stop to start transitions. For stop to start, we're going to use inertialization and have a duration of 0.1. For start to stop, we are going to again use inertialization. The dead blending allows us to use it a bit more and have a duration of 0.15, which is what it is already set to. Let's go ahead and look at stop to idle. In this case, we're going to have a duration of 0.75 and we're going to be using inertialization. And now I'm going to delete out my current logic and again use the was anim notify state active in source state node. I'll select the exit state animation notify state, compile, and now I'm going to go ahead and find the stop animations. And I'm just going to open all of these up. I'll paste the same exit state notify in, but I'm going to reduce it to a duration of 0.25 seconds. And I'll zoom in as much as I need to get that accurate. There we go. Copy it. And paste it into the ends of each of these. Next, let's look at the cycle to stop transition. It has a duration of 0.5 and it is an inertialized blend with the profile of fast feet. So everything matches up here, including the mode with the curve here. Let's look at spin to stop. This should have the exact same settings, so we're going to change it to inertialization, fast feet 0.25, and Hermite cubic in out. For cycle to spin, we are going to make this again inertialized. We're going to give it a duration of 0.2 and a blend profile of none and a type of Hermite cubic in out. Now let's go through each of these spin to cycle transitions. These are going to be inertialized. So for the one that uses the automatic roll, we're going to have a duration of 0.25. For the one that checks the locomotion direction and sees if it's equal to the previous one, again, inertialized with a duration of 0.25. And finally, we have the last one, which is when the gate is changed. That's going to have a duration of 0.2, and it is going to be an inertialized blend. Finally, we have the pivot and tree transition. And this one is going to have a duration of 0.2, and it is going to be an inertialized blend. Next, we have pivot to stop, which is going to have a duration of 0.25, again, inertialized instead of standard, with a fast feet profile as well. So now here we have two pivot to cycle rules. One where we're checking if an animation notify state was active, and one if when we're checking the dot product between acceleration and velocity. I'm going to add a third, and this is going to check if the gate has changed. And what we can actually do is we should have that transition rule elsewhere in this graph. We do, and it is shared, so I can go ahead and use the shared gate changed rule here. Now, for our first transition that checks the animation notify state, we're going to use inertialization. It's going to have a priority of 2, a duration of 0.5, and that is going to be everything for it. For the second, where we check the pivot acceleration, I do want to compare that to my main project, so I'm going to look at that real quick. Okay, I did definitely make some changes here that are worth going over. I'm not using a simple dot product calculation anymore. Instead, I'm getting the acceleration locomotion angle, and I'm checking it against a pivot locomotion angle variable that we have not created yet. So let's go ahead and go into the pivot state. Here I have a setup pivot state function. I'll go ahead and enter into it, and instead of using this pivot acceleration 2D variable, I'm going to go ahead and delete it out. I don't believe we need it anywhere. Let's see if we use it. I'll try deleting it here. Okay, let's find references. And it is in the pivot to cycle rule that we're replacing, so we can delete this variable now. Actually, it's saying it is still being referenced. Strange. Well, I'll leave it there for now, though I do not believe it is needed anymore. And I'll go ahead and get our acceleration locomotion direction. Angle, I misspoke there. And I'll promote this to a new variable named pivot locomotion angle. I'll go ahead and copy this here, and now I'm going to create a new function to bind to the onUpdate binding of the output animation pose. I'm going to name it update pivot state. And here I'm going to get our character velocity 2D and our acceleration 2D. I'm going to normalize each of these. And get the dot product between them. I'm going to check if it's less than 0. And I'm going to get a branch. If this is true, we need to update our pivot locomotion angle as we've just pivoted again while we were already in the pivot state. So I'll go ahead and paste. Whoops, I copied the normalize, so I don't have the code from the setup pivot state copied again. So I'll go ahead and copy that back into the update pivot state and paste it. All right, I'll compile, save, and back out. Now we can go back to that transition rule, and I'll create the logic and then explain how it works. And previously, I ran into occasional issues when entering into a second pivot while pivoting at an angle, or just pivoting at an angle. It didn't seem to always detect or work, and it is an issue that is there in Lyra as well. And this change, from what I've seen, fixes and addresses that issue and allows for pivoting at any angle. And Lyra, it wasn't super noticeable because the deceleration and acceleration values are higher, so the pivot lasts for less time. But using the UUS animation set in this project with those values and the third-person character being lower, it was really obvious in just certain situations with certain timings of button presses. I didn't catch this before I made the video on pivots, but I did catch it afterwards. So now we have our acceleration locomotion angle. I'm going to get the pivot locomotion angle, and I'm going to subtract it from the acceleration locomotion angle. This will just get the difference between both of these angles. So we're going to check the difference between our acceleration and pivot. The pivot only gets set when we pivot and isn't being changed while we're pivoting. So this is the locomotion angle as we were entering into our pivot, and this is our current locomotion angle. So we're going to get the absolute value of the difference, and if that is greater than 50, so if we've changed our acceleration input and the angle of it is greater than 50 degrees away, is further than 50 degrees away from our pivot entry locomotion angle, we are going to exit into the cycle state. Again, this is going to be inertialized, a value, a duration of 0.2, it looks like. Gate changed is going to be a duration of 0.2, and it's going to be inertialized. And it is going to have a priority order of 3. The was anim notify state active is going to have a priority order of 2, which it already has, a duration of 0.5, and it's going to be inertialized. So all of these inertialized. Okay, and that's going to be it for the locomotion state machine here. Let's move over to jumps and compare. I don't believe I've made any changes to the durations of the transitions here. I did not. All right. However, I do believe that all of these can be made to be inertialized. Just want to try to select the ones that are only leading into states and thus have transition time, so I can change these all together. There we go. Set that to inertialization. Okay. Next we have the stop state to look at. Our update stop state function. We're going to change the root yaw offset mode for stopping to accumulate. All right, let's go ahead and look and see how things are looking. So the pivots appear to, well, be reversed. That's interesting. We can actually go back and fix that. We'll do that now. I'm curious as to why that happened. Well, we will address that later if we need to as we compare our other animation blueprint. Something we did between now and then caused that to change, but I believe that I'll address that as I compare the animation blueprint based animation blueprints. So that is going to be it for the base animation blueprint. Now let's move over into the locomotion layers. I did misspeak and refer to the locomotion layers as the base animation blueprint just now, so sorry for that confusion. Now we already addressed the full body additives layer, and I'm going to compare each of these layers in sequence. So I know the falls are all updated properly, and jumps as well. So let's move straight to the spin layer, as it is the top one here. Now this all matches up properly. However, I did add stride warping into the spin in my version of the project. I'll go ahead and go into the cycle state, and I'm going to grab its stride warping node. And I said cycle state when I should have said cycle layer. And now I'm going to check the orientation warping settings for this state. They all match up at the current values. So we can now move on to the next layer, which is the pivot locomotion layer. Let's look at the transition values here. We want to set this to inertialization with a duration of 1.5 Hermite cubic in, out, and fast feet. So now let's go into one of these states. So let's move on to the setup pivot anims function and compare. We're going to set the sequence with inertial blending and set the explicit time to 0. That's right. And for update pivot anims, let's take a look. This is definitely the more complicated function of the two. All right, I'm going to go ahead and copy this bit of code here that gets the dot product and checks if it is less than 0. I'm also going to get a branch, and we're only going to update animations if this is less than 0. So I'm going to plug this reroute node here into the branch. I'm just going to move all of this stuff. Whoops, did not mean to move the distance matching node that's down there. Let's see if we can't figure out how to make a bunch of extra room here. So if that first branch is true, we're then going to evaluate and see if our desired animation based on our function matches the animation we have already selected. And I'll plug the true output of this last branch into the current branch that we are working with now. And I actually made a mistake in the previous video, it looks like. I left the select pivot anim function in for the set sequence with inertial blending node here, when we should be using the new select anims by direction and gate with variable start foot function. And that may have been what was causing our issue. I'm surprised I missed that. It was definitely a mistake on my part when making that video. Finally, we're going to get the sequence evaluator, and we're going to set the explicit time of the animation to 0. We're distance matching to a target, so it'll distance match as it needs to for this half of the animation. I additionally forgot something in the pivot. We need to use the acceleration-based locomotion direction for selecting our animation. And I'm going to need to make the same change in the setup pivot anims function. And that is going to be all the changes to our update pivot anims function. So let's move on to the next layer, and that is going to be the stop layer. So what we want to do first is we want to adjust how we're applying the lean turn additive and lower the intensity as we slow down, so that we don't lean if we quickly turn the camera while stopped before we're fully into the idle state. So we get our lean angle, and what we're going to do is we're going to multiply it by a new float that we're going to calculate here. And we're going to calculate it by getting a few more properties from the main animation blueprint. We're going to get our character velocity 2D. I have to remove the binding before I can select something properly. And I'm going to get our max walk speed. Where is it? There it is. Okay. So now I'm going to get the length of this vector, and I'm going to use a safe divide node to divide the length of the vector by the max walk speed. We can now multiply the lean angle by it and plug that into the lean angle input of the blend space. So now let's look at the setup stop anims function. I believe this should match because the recent video that I did, we reworked the animation selection logic almost entirely. We actually do need to swap this out for a set sequence with inertial blending, as we're now using inertial blending everywhere. Alright, finally we have our idle layer. We're going to change the max transitions per frame to 1. Let's look at the set up turn in place anims function. And let's look at our select turn in place anim function. I did make some changes here. Or I might just have grouped the nodes a bit differently. Nope. Okay. Yes, it looks like I did create some more controls and settings for this. So let's look at this one section at a time. we were first going to get the main animation blueprint, and I also get the root yaw offset from it, and I also changed the evaluation order, going up from the smallest to greatest, so it should always more properly select an appropriate turn-in-place animation. We're going to subtract 45 from the root yaw offset, normalize the axis, and check if the absolute value of the normalization is less than 50. That will be plugged into a branch, and we're actually going to add an AND node on here. And I'm going to create a new variable, and this is going to be named useTurnInPlace 45 for 45 degrees. I'll plug that into the condition, and I'm going to move that variable up into the animSetIdle category. I'll go ahead and copy it, as we're going to have a useTurnInPlace 135 and a useTurnInPlace 180 variable, and will always require a turn-in-place 90-degree animation, so there's not going to be a toggle for that, but there will be for 45, 135, and 180. So now, if this is true, we're going to return the turn right 45 and turn left 45. And I'm just going to scrap the rest of the logic here that we have so far, and I'm going to copy the new logic. Paste, and plug the entry of the branch into the false of the previous branch. So now, instead of subtracting 45, we are going to subtract 135. We're going to swap use 45 for use turn-in-place 135, and we're going to return turn right 135 and turn left 135. We're going to paste again, connect it up, and this time we're going to subtract 180, and we're going to use the use turn-in-place 180 degree boolean, and we are going to output the right turn 180 and left turn 180 animations. And finally, we're just going to copy the return logic here and output the 90 degree and do no check, because we always have to have a 90 degree animation now in this system. So left 90 and right 90. That's going to be it for updating the select turn in place animation function. Let's check the transitions for the state machine now. We're going to use a standard blend for turn-in-place entry to turn-in-place recovery with a duration of 0. The transition rule is checking if turn yaw weight is nearly equal to 0. That matches up. Now let's look at the turn recovery to turn entry. And we're checking if the absolute value of root yaw offset is greater than 50. So that matches up properly. We're going to be using inertialization for this transition with a duration of 0.2. And let's look at idle to turn in place entry now. The logic does match up, and the timing should be 0.2. We're using a standard blend here. Turn in place recovery to idle. In this case, I've found that the automatic rule doesn't always work, or didn't always work for me. So we're going to use the was anim notify state active in source state function again, and this time we're going to use that same animation notify state exit state animation notify state, and that is a lot of saying animation notify state. And let's look at the duration. We're going to do 0.35, and we're going to have the type set to standard blend. Okay, so the last thing we're going to do is go ahead and make our way to the turn animations and add that exit state animation notify state into these. And it looks like I may already have these in. I do. All of the animations are now working properly. The pivot animations are being chosen properly. now that we have switched out the input variables for the selection evaluation. Additionally, the pivots at angles are working, and it is choosing the right one and applying orientation warping in, I think, a much smoother manner now than it did before. Additionally, the overall smoothness, I think, has greatly increased in the system since we switched over to dead blending with inertialization in Unreal Engine 5.3, as opposed to just the normal inertialization in Unreal Engine 5.2, where we had to use the mix of standard and inertialized blends. So overall, I think the smoothness is much better than it was before. All right, one last thing that I did forget, and that is the base animation blueprint. And let's go over to the cycle to spin transition. This is a transition that I forgot to check and compare, and I do remember that there is something that we need to address here, and that is to make use of the enable variable hip facing boolean that we've previously created. I'm going to add a condition onto the and node and get the enable variable hip facing boolean that we created. So if I make this true, and the pivots do match up now, we'll do that spin. To align the hips properly, I can set it to false. Compile. And now let's change our desired hip facing so that left is backwards. And we're going to stay in that backwards facing animation. So moving from forward to left, it'll just switch to the backwards facing and not do the forward facing. Same is true for backwards to right. It's just gonna operate off of the desired hip facing. And so you just fill in the animations that you have, and like where you have like left backwards to left forwards, or however much, you just put in the animations you have and make sure all the animations are filled in, and just substitute incorrect animations that might not match up in case something gets used, but it should only use the animations that correlate with the ones that your pack should have. If you do run into issues with it going into an A pose, you can just fill in the empty pivots with the ones that you already have.
All right, everyone, that's going to be it for this video. You can access the project files for this tutorial series with guaranteed continued support and future updates over on patreon.com/OutcastDevSchool for $10 a month. I want to give a special thanks to my patrons over on Patreon for their continued support, and I'll see you all in the next video. Thanks for watching.